Yeah, I'm really happy to be here. And, we already heard a lot of wonderful lectures by, say, Robert Dagraff and Andrei Bernwick and Natty Seberg. So they already introduced a lot of a concept and a notion which I'm going to use. I'm very happy to, to talk after that. After them, also Nick Reed going to talk about these fractional quantum Hall states, which also relate to something what I'm going to talk about. So, so in these three lectures, I mainly try to discuss so-called gap quantum state matter. But certainly, the quantum state matter have a gapless one and have a gapped one. The gapless one are very difficult, and we don't know how to do it. But that certainly is more interesting, actually. It's one of a interesting, challenging project, and the young people should really get hand on. But for me, it's very scared. So I will do the simple one, the gapped one. The gapped one is much simpler, and so maybe we can have a classification. But certainly, the gapped quantum state matter have a symmetry breaking one, which we understand pretty well. But also, we have something beyond the symmetry breaking. Even without symmetry breaking, we have a many gapped state. And then for among those which do not have symmetry breaking, we have so-called long-range entangled states, which do not need any symmetry, which called topological order. I think the fractional quantum Hall state Nick going to talk about will belong to this class. And also there's another class which have no topological order. It's only short-range entangled. But this class requires a symmetry to have non-trivial examples. And today, I will mostly, not today, these three lectures I will mostly concentrate on this kind of a gapped phase. But at the beginning, in this lecture, I will kind of discuss the gap phase in general and discuss this part, but very quickly only state some result. And then we'll go into some details to discuss this short-range entangled symmetric phase more slowly and more carefully.
Are long-range entangled, is that a specific case when the group is trivial of SP?
No, I will explain that notion. Yeah, so it's just to give you some big picture, and certainly, what is a gap state? So, that's very simple. Well, you have a spectrum with with a gap. That's it. But actually, it's a highly non-trivial issue. What is a gapped state? And the reason is that in order to define gap state, we need to take thermodynamic limit. Because for any finite system, the spectrum are discrete. They're always gapped. There's no gapless spectrum for finite system. And taking thermodynamic limit is very easy. You just repeat Hamiltonian. But actually not. If you do not require any symmetry, including translation symmetry, suppose you do not have translation symmetry, then taking thermodynamic limit is very, very tricky. We don't know how to repeat Hamiltonian. There's no way to repeat Hamiltonian. So to define thermodynamic limit without translation symmetry is one of the challenge which I'm going to kind of tackle here. And that's one thing. Another thing we know that the gap state, well, so-called gap state, may have a gapless boundary. So when you actually put the system on the disk and do the computer calculation, you don't see the gap because of gapless boundary. So there's another subtlety. Okay, this can be easily handled by putting the system on the space manifold which have no boundary, like a sphere or torus. But then it's also not desirable. Then your definition of a gap state would depend on the topology of a space where you put your system on. And we don't want that because in our sense, a system is local. We don't need to know the topology or boundary condition to say whether this system is gapped or not gapped. So we don't want to put the system on torus or genius Riemann surface, things like that. We like a disk, it's local. But the disk, you have to handle the boundary. So that's another difficulty we have to handle. So why we want to do this? Because if you want to set up a mathematical foundation to describe gapped states, you need to know what is the input. We know what is the output. Output is a classification of phase of matter. But what is the input? So by carefully defining this concept, we can help us understand what is the input to even define a gapped state of matter. And then the mathematical definition of setup would take those input. You have to take proper input so you can set up a proper theory. So that's why I kind of go through this. So since we are consider a system without transcendental symmetry, so we can put a system on the lattice with which is kind of random graph. We could have degree freedom on the vertex, on the edge, on the face, and etc. But here, for simplicity, I will only put the degree freedom on the vertex. So this led to this notion of a local Hamiltonian. A local Hamiltonian really means that the Hilbert space is a direct product of a small Hilbert space which defines an anti-lattice site. And this definition essentially gives us this locality. Then the Hamiltonian is some operator which only acts on a single site or neighboring site Hilbert space. So that's a usual definition. And so this is a local mean. So the system we consider always local, have this local property. And in high energy physics, this may be one version for UV completion, which is a very important concept. So because we define this local Hamiltonian on the lattice, so in a sense, the theory we define here always have a UV completion, which we call well-defined, and which in another name is anomaly free. We'll come to that later. So this is local. So what is gap? But here I say the gap would mean the bulk gap. So in the simple English is that the excitation in the bulk are all gapped. So this is what I mean by gapped. And in a more precise mathematical definition is the following. Is that, so suppose we have a spectrum like this. Then below certain energy gap, we have some low-lying excitation. Then we say that the matrix element of those low-lying states for the operator which is inside the bulk are all the same. Means suppose we have a ground state, we have a matrix element for the ground state, we have a matrix element for the excited states. This average operator for the ground state and for the excited states are the same for all the local bulk operator. So the operator, this OX, are inside bulk, have certain distance epsilon c away from the boundary. Then the error you make is exponential small compared to this distance to the boundary. So this is a more precise definition of the bulk gap. Basically, we do have a gap excitation, but however, the gap excitation only changes the wave function on the boundary. They do not change wave function in the bulk. So that's a way we say the gapless excitation are near the boundary, nothing in the bulk. And this definition, there's another way to say this definition. You say that all the low-lying states below certain energy gap are locally indistinguishable in the bulk. Means there is no local operator in the bulk which can distinguish those low-lying states. But certainly operator on the boundary can distinguish them, but nothing on the bulk can distinguish them. So that's another way to say this bulk gap. That's the meaning. Okay, so this really define this system. But remember, this definition actually works for finite system. I've been careful to formulate this definition so that those statements can be made even for finite system. So before we take thermodynamic limit, yes.
What does it mean that they are indistinguishable? If they have different energy, then Hamiltonian distinguishes them.
You have different energy. No, so these operators are local operators. These all are local operators. So they only act on the Hilbert space in the middle, on the site near the middle. the Hamiltonian contains terms everywhere. And, but however, when we do this average, we only consider the local operator. The average of a local bulk operator are the same for all the low-lying states. Yeah. So with this definition, now we can take a thermodynamic limit. So because of the definition we have here, we define so-called the gapped state or gapped Hamiltonian or one system, a particular system. So now we can take thermodynamic limit. And to define the gapped phase. Okay. So what is a gapped liquid phase? So this is a definition. So gapped liquid phase is an equivalent class of a sequence of a bulk gapped local Hamiltonian. So bulk gapped local we have defined before. So this is bulk gapped local Hamiltonian. It has been defined in the last transparency. And then we have a sequence of this kind of bulk gapped local Hamiltonian. So that's a thermodynamic limit. When you have a sequence of a Hamiltonian where size go to infinity, that is thermodynamic limit.
Are you changing the number of lattice sites?
Yes.
Or fixing the lattice?
No, changing lattice size. So the size of system increase. This nk is the number of lattice sites. And we keep increasing and nk go to infinity. So that's this nk is the lattice site, so we go to infinity. And this sequence is we take thermodynamic limit. So therefore, a thermodynamic limit of the system is not a single Hamiltonian, it's a sequence of a Hamiltonian. Okay. Yes?
Sorry, when you define local operators, do you choose a particular lattice?
Yes. This is the first thing. You know, we first have this tensor product structure. The total Hilbert space is a tensor product local Hilbert space. This structure is there from the very beginning.
No, my question is that then, say if I have a periodically symmetric lattice or something, then how do I know that which lattice I need to take, like the position lattice or the momentum lattice?
There's no such thing as a momentum lattice. I'm always talking position lattice.
Okay.
So these are real space picture. So this is crucial. We don't do Fourier transformation here.
So whenever you say local, it's safe to assume that you're talking about local in the sense of real space.
Of course, yeah. Just like a sheltering interaction means sheltering in the real space, not sheltering in the K space. So I'm using this usual language here. Yes.
Why do you call it liquid?
Okay, I need to explain. That's the next. So first, I just explained thermodynamic limit is a sequence of Hamiltonian go to infinity. That's it. But this sequence only describes a particular state. As a phase, the phase means an equivalent class of states. You know, different states can be equivalent. We say they are in the same phase, so they are equivalent class. So how to define this equivalent class? Well, that's very easy. That's because we can gap the system. If you can deform the Hamiltonian without closing the gap, then that's in the one equivalent class. And here, the more formally, you can say that if two sequence Hamiltonian, like we have one sequence, we have two sequence, that's a two sequence Hamiltonian. If these two sequence Hamiltonian can be connected one by so-called local unitary transformation, then we say that's a one-over equivalence relation. Local unitary transformation means that we perform unitary transformation among nearby qubits, only among nearby qubits. And we may have some layers. So each box is a unitary transformation among, say, like 4 qubits. And we have many, many boxes. And we may have several layers. But number of layers is always finite. You know, it can be large, but they do not increase as system size go to infinity. So always this number of layers is uniformly bounded regardless of the size of the system. Okay, so that is an equivalence relation. But that is not enough. So there's a 2 papers. So originally we think, oh, this is a definition, but later turns it's not enough. We need another definition, and this definition really corresponds to this liquid. This liquid relate to the second definition, the second equivalence relation. There's another equivalence relation, and this equivalence relation is needed because of the following. If you only have this kind of local unitary, you can see that we do not connect system with different size. And this is worrisome. With the translation symmetry, there's no problem. We can always repeat the system to make system bigger. But without translation symmetry, changing system size is very tricky. It could be, for one size, we have a quantum Hall state. In another size, we have a topological insulator. Without translation symmetry, anything can happen. So we have to have a way to connect the Hamiltonian with a different size. So how to do that? Well, so that's where the second equivalent relation comes from. That basic naive, the mathematical formula is hard to understand. The picture is much better. So we have a system with smaller size. Then we just add the product states, make the bigger size. Then we say that these two systems with different size, these have a product states added, are equivalent. That's one of the equivalence relation. So mathematically, we say that the Hamiltonian with the one size are equivalent to another Hamiltonian, which is the original Hamiltonian, tensor product, some trivial Hamiltonian, whose ground state is a product states. So this is another equivalence relation. Then the combination of these two equivalence relations together will link both horizontally and vertically. And so this gave us a proper definition of a so-called gapped liquid phase. So liquid really means that it can dissolve any product states. You can add a product state to the system, and the system can absorb it, and seamlessly and become a system with a bigger size. So this kind of way to take thermodynamic limit. Yes.
Do you have to show that HTRI or trivial is like unique up to some equivalence? Like, well, why do you pick that?
Yeah, we can pick it up, but this one is a connect other choice. So that's mix the two. These are generator of a two equivalence relation. When you compose the two, you get everything. Yeah. Yeah.
So is the second tensor product the only way to connect different sizes?
Yes. So this is actually this is pretty important. So that's give us liquid nature. Yeah. So when I try to explain this, I really try to limit the thing we discuss. We are not only talking about gapped state or gapped phase, we are talking about the gapped liquid phase. So satisfy those kind of conditions. So this is the topic of this lecture. We consider these kind of states. Okay.
You've got no definition of, or I haven't seen any like notion of adiabatic continuity here.
Yes.
So I assume, is this because we're not talking about symmetry protected stuff, and so you can assume if you have a local unitary, it's possible to find some adiabatic definition that
Yeah.
preserves
So here, the definition, I'm not using symmetry yet. We can later we'll put in symmetry, but here no symmetry. The adiabatic deformation or evolution is the first equivalence class. So the two Hamiltonian, which are related by this first local unitary, can deform into each other adiabatically without closing energy gap. So we hope this is theorem. It's at least conjecture. So this one is related to the usual adiabatic evolution. So that's a definition A. The definition B is a little beyond that. Yeah. Yes.
So in some papers, like talking about quantum spin liquids, this term like liquid phase, it means like the ground state doesn't break any symmetries. Is that related to what you're talking about?
Yes. I'll come to this point. Yeah. So with this definition, we say that we hope this equivalence relation is not too powerful. So we do have a distinct equivalence class. Okay. This distinct equivalent class will be, we call this a gapped liquid phase. Okay. And this distinct equivalent class of gapped liquid phase actually is nothing but this topological order, which was defined in a little bit different manner. I will probably cover that in a moment. And but this definition, this kind of point of view actually related to the entanglement. It's really kind of entanglement point of view. So this distinct gapped liquid corresponds to many body system with different pattern of a long-range entanglement. So this is the definition of a long-range entanglement, what I try to define here. So why are you using entanglement? Because certainly we can start with the product states. So there's one class of one equivalent class which contain product states. So something which are local unitary equivalent to product states. And this we call the short-range entangled states. And that's very natural because the products have no entanglement. When you do local unitary transformation, you locally scramble the entanglement. So you locally have some entanglement. So anything connect to product states by local unitary transformation, we call short-range entangled. But not every many-body state are short-range entangled. There are certain many-body states which cannot be connected to product states. So those many-body states are called long-range entangled. So that's this yellow part, this long-range entangled. But there are different types of long-range entanglement. So this part do not connect to short-range product states, and this part do not connect to short product states. But these two parts do not connect to each other, so they belong to different phases. So these two, we cannot change the state here to here using local unitary or adiabatic evolution. So this really define the topological order or long-range entanglement. So that's a basic picture. So those are very, very abstract. So let's give some example. But let's give first some concrete example. What is the example which is not gapped liquid? First, the symmetry breaking state is not gapped liquid in this definition. In the paper I wrote before, the symmetry breaking state is a gapped liquid. But now I changed the definition a little bit. This new definition excludes symmetry breaking states. So why symmetry breaking state is not gapped liquid? Because it is local indistinguishability. You can see in the bulk gap property, I say all the low energy states are locally indistinguishable in the bulk. When you have a symmetry breaking state, like all spin up, all spin down, these two degenerate states are low energy states, but they are distinguishable in the bulk. So this local indistinguishability rule out the symmetry breaking state. So symmetry breaking state is not included in the gapped liquid, which is a little strange, but that's fine. And a non-trivial example of a non-liquid is that it's a 3D layered quantum Hall states. When you have we know quantum Halls are two-dimensional topological states. But when you have many, many layers, have a three-dimensional layered quantum Hall state, I mean fractional quantum Hall state, very important. Yeah, I should add fractional. Integer may be tricky. The fractional quantum Hall states. And then these states cannot increase the size by adding product states. Suppose you start with a smaller size system with 100 layers. You want to double the linear size system. When you do that, you're supposed to get 200 layers. But when you try to add a product state to increase the number of sites, then this way you can enlarge the system with the same size, but the new system still have 100 layers. So therefore, these layered quantum Hall states fail this equivalence relation of dissolving these product states. It cannot dissolve product state by increasing the size. So the layered 3D quantum Hall states is not a liquid, but it's a gapped state. It's usually we call the gapped state. But maybe in the Euro terminology, we do call that gapped liquid. But in its more precise definition, it's not gapped liquid. And a more non-trivial example is Hart's 3D cubic code. And for those who know it, it's a gapped state. It's not liquid. So therefore, the theory of topological order do not apply to Hart's 3D cubic code. Yes?
So just to understand the terminology, if you look at the topological field theory, like Chern-Simons theory, 2+1 dimension,
Yes.
that's qualified?
That's a liquid.
Yeah. But if you take the same system and you compactify it on a circle, and you look at low energies in 2 dimensions, in 1+1 dimension, does this qualify or not?
That's also liquid. You mean you have a two-dimensional Chern-Simons theory, you compactify to the circle to get 1 + 1 dimensional theory, that's also liquid.
But then you can distinguish by the thing that would be a local operator with 1+1, which is non-local with 2+1.
Yes, so that means their topological order or something could be different because the definition of local operator is changed. So whether what you call long-range entanglement or not long-range entanglement became tricky. So actually, this is a very good example. as a two-dimensional system, this Chern-Simons theory of quantum Hall states have a Lagrange entanglement. When you compactify on the circle to make it a 1 + 1 dimensional reduced theory, this dimension reduced theory have only short-range entanglement. It's always equivalent to the product states once you do that. And that's precisely because some non-trivial string operator now became local operator when you do dimension reduction. Then the locality is changed, so this Lagrange entanglement also changed. Yeah. Yes?
Why did you layer the quantum Hall state? Just to be in 3 dimensions?
Yeah, just in 3 dimensions.
And likewise for the cubic code?
Cubic code, we don't even know. I think have a layered structure, but it's much more implicit. The Hamiltonian is pretty isotropic. And so on the first side, if you look at the Hamiltonian, it's just like a KTS toric code, some kind of spin operator. But amazingly, it's not a liquid, you know. And so actually, this the reason we go into liquid, this dissolving product state, is mostly motivated by trying to understand the Hart's cubic code, because Hart's cubic code do not fit into this tensor category formulation. And so we need to find a way to exclude that. So gapped state is very complicated, but the gapped liquid are simple.
I don't understand why the quantum Hall state doesn't fit your definition.
No, quantum Hall fit. But
Counterexample.
no, 3D layered quantum Hall state means quantum Hall state is I should say 3 + 1D layered quantum Hall states. And quantum Hall state is 2 + 1D. As 2 + 1D is a liquid. But you can stacking many layers to form a 3 + 1D state. And as a 3 + 1 dimensional system, this is not liquid.
Why?
Because it cannot dissolve the products. Because this number of layer is something important. For smaller system, you may have 100 layer. In the bigger system, have 200 layer. But from 100 layer to 200 layer, you cannot change that by adding product states. Yeah, so you cannot dissolve product states to make system bigger. You have to add non-trivial things.
Why can't I cut each layer into 2 parts and somehow stack them? Is this non-local or what?
This is not part of the definition. You know, our definition is you add a product state to increase system size. That is the only way to increase system size.
But by cutting it and restacking them, I'm not increasing the system size. I just increase the number of layers, making each one smaller.
But this is not a part of equivalence relation. You can say I only have these 2 equivalence relation to define equivalent class. Now you introduce a third operation. And when you redefine the equivalence relation, then the things are different. So
Saying that this restacking thing is not an LU?
no. Yeah, the LU is just like you have the same state. You don't change the lattice size. You just perform local unitary transformation locally. You don't change and reshuffle lattice size. Yeah. Yeah. Actually, you know, what you said is very good, actually. You don't have to follow this definition. You can invent your own definition. Then you have your own definition of phase matter. And when you come up with the right definition, you may get a very good mathematical structure. Yeah, but here I just using one definition. Another comment here is the following. This liquid phase is necessary so that this gapped phase can be described by so-called TQFT, topological quantum field theory. Yes?
So, but your thing with you can't go to increase the number of layers, what does that have to do with the quantum Hall effect? Any 2D system, you can say you can put in product states and it will increase the layer, but not the number.
No, as a 2D system, you can add a product state to increase system size, and you still have 1 layer.
But any 3D system which is composed of 2-dimensional
Yeah.
layers, so it seems that your problem with the layers of the quantum Hall state is that you can't you don't increase the number of layers when you add product state. But then any 3D system if it's composed of 2D layers, it would seem like your argument is the same.
Yes, and let me see. This is related to this. Yeah, to explain this a little tricky because the fraction quantum Hall state are so-called non-invertible. We will talk about this, but maybe let's talk private because of this. I just want to say that the layered quantum Hall state is not a liquid because when you in the natural way to take a subordinate limit, number of layers increase. But however, this kind of increased number layer cannot be connected via adding product states. And this is requirement to be a liquid state. The system with different size should be connected by adding product states. And this requirement actually is a requirement that this gapped phase of matter can be described by quantum field theory. Somehow, that's my feeling that the quantum field theory only describes this liquid-like phase, only describes phase which can dissolve product states. The quantum Hall state, layered quantum Hall state, if you want to do quantum field theory description, you find you need an infinite number of field. The number of field depends on system size. And this is a typical sign that if you allow this kind of quantum field theory, then it's okay. If you only consider quantum field theory, which only find a number of field for any size of a system, then this kind of quantum field theory probably can only describe liquid states. And the non-liquid states, those examples probably need a more special kind of quantum field theory whose the number of field increase with the system size. And so there's maybe another type of quantum field theory. So this is also this is very interesting. So topological order is not everything. So those are things that are beyond the topological order. They have even more complicated, richer entanglement structure. And, but this is not what we are not going to talk about this. Yeah. But this, again, this is another very interesting future direction to go into. So now let's give some example of a gapped liquid phase. So certainly the product state is one example of a gapped liquid phase. But this is trivial, it's a trivial states, okay. And other are kind of non-trivial. For example, this 1 + 1 dimensional P-wave superconductor. This is Marana chain. I think Andrew Benedict talked about in his first lecture. And this 2 + 1D P + P superconductor, again, Andrea talked about this. And it's the work done by Reed and Green. That's another fermionic gapped liquid phase. And certainly integer quantum Hall states, that's also yet another one. We have been seeing that. And the fractional quantum Hall state, I think Nick Reed is going to talk about this. And but all those are kind of fermionic example. And the bosonic example, actually they are seen by experiments. All those examples probably seen by experiments. You know, these first two are still, people are trying. But there's a bosonic version. So that means this gapped liquid phase formed by bosons. And one of the first example is a chiral spin liquid. The chiral spin liquid basically is like a fractional quantum Hall state for bosons. And so actually, recently we see that there is some simple model, some two-body Hamiltonian model, which can realize chiral spin states. Like we have a spin on the Kegelman lattice. You know, so the Kegelman lattice is so the corner Xiao-Gang triangle. So we have the nearest neighbor is the J1.
Can I suggest the other blackboard?
Oh yeah, this is a. So nearest neighbor is a J1, and I think this second neighbor is a J2, and now we have this third neighbor will be the J3. So we have this Heisenberg coupling of a nearest neighbor, second neighbor, and third neighbor coupling, and yeah, now I can think of the light. So we have this kind, but actually if you add just a kind of like more than 10% of a second neighbor and third neighbor coupling, this Kegelman lattice Hamiltonian will go into a phase which is actually realized is a chiral spin liquid. And this kind of material are available, but the third neighbor and the second neighbor coupling may not be this form. So we don't know. Yeah. But anyway, this make it kind of hopeful. Maybe you can realize chiral spin state. And also another bosonic one is a Z2 spin liquid, which are simpler than chiral spin states. And then there's so-called non-abelian quantum Hall states, like the Pfeffing states or SU2 level 2 states. The Pfeffing states, like a pure paired states, in the p-paired quantum Hall states. And SU2 level 2 states is described this kind of wave function. That's this nu equal to 1 integer quantum Hall state wave function times a nu equal to 2 integer quantum Hall state wave function times another integer nu equal to 2 integer quantum Hall state wave function. And this kind of product of 3 wave function gives some kind of antisymmetric wave function which happen to describe these SU2 level 2 states. And these 2 states are really special because all the previous examples are abelian, and these last example is non-abelian. Actually, they actually have a same non-abelian statistics described by icing cross U1, another is icing cross U1 square. And this icing is exactly what Andrea talked about in the last lecture. This you have a sigma, you have a chi, psi, so that kind of non-abelian statistics. So which actually realize in these 2 examples. So that's some kind of example. So actually we have we have many examples of this topological liquid. So the question is that can we have a systematic understanding of all those examples? So what I have described, just give some examples. But now do we have kind of a big picture? We have a list of a complete table of all these pattern for long-range entanglement. So this require a quantitative description of a pattern of entanglement, so or topological order, something quantitative. And you may say, okay, the quantitative description is very simple. You just write down the wave function. If you know the wave function, you'll know the states. But the wave function is a pretty bad quantitative description because it's many to 1. Many different wave functions correspond to the same entanglement. So we want to find more or less a 1-to-1 description. What is a 1-to-1 quantitative description of all those patterns for entanglement? So this kind of proposal, this proposal of the 1-to-1 description is actually used to introduce this notion of topological order. So one of data is a ground state degeneracy on sphere, torus, or genus Riemann surface, and etc. So those topological states may have a non-trivial degeneracy on those compact space. So those degeneracies are special because those degeneracies are robust against any perturbation, any local perturbation. So that kind of very special topological degeneracy. And another thing is a geometric phase, abelian or non-abelian geometric phase. When you deform the Hamiltonian on the space. So to the energy physics, I can say I can deform the metric of the space. When you deform metric space, you deform the Hamiltonian, and then you may have a geometric phase, either abelian or non-abelian geometric phase. So we can also use this geometric phase as data to quantitatively describe this pattern entanglement. So this is basically just these 2. One is a ground state degeneracy, another is a geometric phase of deforming the Hamiltonian to condensed matter physics or deforming the metric to energy physicists. And so the first deformation is we call the local deformation. Yeah, maybe you need some lights here. So we have this. So we have some kind of space, okay? Then we just deform this another space. We just deform it. So this give a time direction. So we just deform it, and then we deform it back to the same shape. Then glue this together. So this process gave us a loop, and this gave us a geometric phase. Because ground state, when you deform the loop, there's maybe a phase associated with it. Yes?
Each of these slices is from your earlier definition. This sequence of Hilbert spaces, right? And
each slice is a Hamiltonian. So this is a Hamiltonian, but they may have a time dependence. So we consider time as a parameter. We consider this the T parameterized Hamiltonian. And each Hamiltonian gives you ground states. Then you get the T parameterized states. Then these T parameterized states go around the loop would give us a geometrical phase.
Right, but these slices are corresponding to my physical system. I have this lattice.
Yes.
And I'm taking the thermodynamic limit. Right?
Yes, yes. So each slice is a lattice. But this Hamiltonian may depend on this parameter T. So we're changing the Hamiltonian continuously. And so this is what you do. And then we have the phase, this geometrical phase. But this geometrical phase can be written as actually it's a partition function. This is really some kind of partition function, and which is a kind of some kind of effective Lagrangian. This is basically a effective Lagrangian you obtain by integrating out all the matter field. The only thing left is the metric of the space-time. So this effective Lagrangian is a Lagrangian in terms of space-time metric. So actually it's a gravitational Lagrangian. And in particular, this Lagrangian may contain, now come to this, may contain this gravitational Chern-Simons term. So that's the one of possible topological term in 2+1 dimension. And so actually this kind of a local deformation can detect, I hope, this gravitational Chern-Simons. I think Nick Reed is going to really talk about this in much more detail in his lecture. So this usually about this. So this local deformation can detect this gravitational Chern-Simons term. And there's a very important parameter. The coefficient in front of the gravitational Chern-Simons term is supposed to be the central charge for the edge states. So that's one of a very important parameter, data. So which can presumably can be detected by this local deformation. And then there's a global deformation. For example, we can put the system on a torus. Then we can rotate the torus by 90 degrees. So that gives us an S matrix. Or we can do a Dane twist of the torus. And then we can also get the loop using Dane twist. And this kind of geometric phase is give us this T matrix. And this actually is a Dane twist and a 90-degree rotation generate this so-called modular group. And these two non-abelian geometric phase, this S and T, became a representation of a modular group, which satisfies this relation. Again, I'm very happy Andrew mentioned this in his lecture. So this kind of structure also appear here. Yes? Okay, yeah, this is a $1 million question. This in 2+1, this works. I hope or I believe in higher dimension it works equally well. But this is a much more unsolved question.
So you put 1 and 2 be generalized? Because both the number 1, which is bound to the energy on
Yeah, certainly in higher dimension, the topology manifold is more complicated. So you have to consider all topology manifold. And when you do this mapping class group, I only do torus in 2+1. I'm not sure in higher dimension one this is enough. You probably have to do many of topology of space. But this idea of using this degeneracy on various topology of space on the geometric phase, again for the deformation with the various topology, I believe those carry all the information of a topology order. So this supposed to be one can using those data to develop a theory of topology order in higher dimension. But now I only do 2 dimension, 2+1 dimension. But that's a very, very good question. So yeah, that's one thing I'm thinking about is how to do that in higher dimension. Yeah. Okay. So those are data. So basically, the data is S and T, and this is C, this Chern-Simons term. And the dimension of S and T actually is a ground state degeneracy on the torus. And so therefore, one may say, okay, and that's it. If you write down the S and T, we get topology order. We have this gap, the liquid phase, and we get the classification. And which, yeah, it's kind of like that. But things are a little bit more complicated. So let me just try to explain one actual feature before I using S and T try to describe or classify topology order. So one actual feature is that there's many kind of gapped liquid or topological order, many kind. And we want to divide this different topological in two classes, a simple one and a not so simple one. So what is simple one? The simple one is the topological order have no topological extension, no onion. That's a simple one. You say, oh, that must be trivial. If you have some topological order, all the bulk extension are trivial, then that means the whole phase is trivial, should be product states. Well, that's not the case. Actually, there's a counterexample. And another way to explain the distinction between simple one and non-simple one is to study the stacking property of topological order. We know that when you stack two gapped states together, you still get the gapped states. So therefore, the topological order admits this stacking operation. So let's this S to be a set of the topological order. Then this stacking will be this box. The box operation is 2 to 1, a binary operation over this set. And this box operation almost make this set into a group, but not quite a group. It make it into called a monoid, which is something I learned last year. And so monoid is basically a group without inverse. So it's a group, except the inverse is not well defined. But I mean, everything else of a group is well defined. It's defined also. For example, the identity is defined. Identity means that you have particular topological order. When you stack that with any other topological order, you get the first one back. And this one is trivial. It's a product state. That's precisely the dissolvability of a product states. So this product state is identity. However, not having inverse means the following. That's when you have one topological order, when you try to stack with another topological order, you cannot find a topological order B such that their stacking give rise to product states. This can happen. Yes? Semi what?
Semigroups don't have an identity. It's the terminology.
Yeah, so maybe my definition, my understanding of mono is wrong, but maybe this is better. Group without inverse. Maybe. I don't know. There's so many mathematical concepts with a slight difference, which I don't know the difference anyway. And so to basically say that there's sometimes a topological order have no inverse, means we cannot find another topological order when, after stacking operation give us product states. And why that can happen? Because suppose one topological order have NA type of onions. Topological order have a non-trivial topological extension. And the second topological have an NB type of onions. When you're stacking the two, the new topological order their onion type will be NA times NB. So always increase. So from here you can see that only topological order which can have an inverse is that is the topological order that have no non-trivial topological extension. So that means NA NB equal to 1 means only trivial extension. There is no non-trivial extension. In that case, NA NB equal to 1. So in this case, the stacking always keep into this in the space where there's no non-trivial topological extension. So that's kind of invertible. Yes?
This statement, if and only if, is supposed to be true in any dimension or only in 2 dimensions?
I think it's true in any dimension. But however, in other dimension, you need to consider loop, a string, or membrane extension. So it means no non-trivial point extension, no non-trivial string extension, no non-trivial membrane extension. I believe that is true in any dimension.
So in 2 dimensions, we only have to consider points? Or
Exactly.
Points or
Yeah, only points,
not strings?
not strings. Yeah, because a string, kind of string is not allowed. But this is let me say, yeah, this is a little bit hard to explain. For the 2-dimensional topological order, which are well defined and anomaly free, then it cannot have non-trivial string extension, because the string cannot be modular. Because the string cannot braid with anything else in 2-dimension space. So if a string is topological, it cannot be modular. The particle you can using braiding to detect any topological particle. Yeah, there's something related to that. So therefore, codimensional one excitation is not allowed in so-called topological order with UV completion. But however, for anomalous one, it's allowed. Yeah, there's a more stuff there. Yeah, but I believe. Sometimes I really don't know how to prove, but I believe this is true in any dimension. But you should need to consider all type of topological excitation. Yeah. Yes.
So once you stack them, are you going to allow for coupling between your two systems?
Yeah, stacking means first without coupling. Then you can add a little bit of coupling without driving phase transition. So coupling is allowed as long as you do not add strong enough coupling to change to make a phase transition. Yeah. Yes.
So firstly, is it easy to see that the invertible topologicals have commute?
Yeah, the stacking is commuting. So this is a commutative monoid.
Okay.
So this operation is commutative.
Yeah, it doesn't seem obvious.
I don't know, it's obvious to me. You can stack AB, and because the thing that the order in the spatial dimension doesn't mean anything. It's just coupling between the two. Yeah.
Stacking means you take the tensor product of the Hilbert spaces and
Yes.
you add the Hamiltonians.
Yes.
So that's manifestly commutative.
Yeah.
and dissociative.
That's true. Yeah. Yes.
So is stacking the stacking even for the ones without excitations? Are they Abelian as well?
What is stacking?
Like stacking in general is like this monoid is in general Abelian. Just doesn't necessarily.
Yeah, the stacking operation are Abelian operation. Yes. Yes.
So once you allow for coupling, then some excitations can be confined, right? So say that.
No, they're not all confined because when you add strong enough coupling to drive a phase transition to get new phase, then the extension is confined. If you add perturbative coupling without driving phase transition, then none of the excitation are confined. You know, the confinement discussed by Andrea in the last lecture is really about you adding in strong enough perturbation to drive a phase transition to get a new phase, which is not stacking phase, it's just new phase. Yeah. Yes? No, it's there are examples where I don't know, either way, you know, topological order without inverse can have a gaplet excitation or can have a gaplet on boundary. No, that's yeah, this is more delicate. Yeah, and so most topological order don't have a inverse. And so actually, so in this table, the blue one are invertible topological orders. They are both invertible, which means there's no non-trivial bulk excitation. They are invertible. Like a fractional quantum Hall state, actually, fractional quantum Hall states are all non-invertible. There's no inverse. Even though you have chiral edge, it looks like you're stacking the complex conjugate of that, you can cancel the edge. That's not true. Yeah, the edge can be gapped, but still non-trivial. And the bulk still have non-trivial excitation. And so that is a. Because have no non-trivial bulk excitation. Vortex is not excitation. Yeah. Is the excitation just a bulk of quasi-particle? Yeah. The excitation just a bulk above quasi-particle, just this fermionic quasi-particle excitation. So you know you have a Hamiltonian. There's a C dagger C. You just diagonalize Hamiltonian. Look at the spectrum. You know, in the spectrum you only see fermions. There's no vortex in the spectrum. So that's what I mean. Topological, the excitation and the topological excitation. So this vortex do not appear in the spectrum of this particular Hamiltonian you write down. This is a free fermion Hamiltonian. You just diagonalize it, look at the spectrum, there's no vortex in it. You only have a quasi-particle, a fermionic quasi-particle in it. So this is qualified that in the excitation spectrum, there's no topological excitation. So all the excitation are trivial, so it's invertible.
Trivial means they have trivial braiding.
Trivial braiding, yeah. For fermion, actually, it's a trivial fermionic topology is a little tricky, but yes, the trivial braiding, yeah. So we view fermion as a trivial.
By the superconductor, you seem to mean just a Majorana fermion without the underlying gauge field.
That's right. Yeah, that's a Euro definition. But if you include the gauge field, it's a different system. Then the things are different. Yeah, maybe I'll make a comment on that. Yeah, if you only have a free fermion Hamiltonian thinking that system, then this is what I mean by P plus P superconductor, just this free fermion Hamiltonian. Yeah. Yes.
For some reason, the microscopic theory does not include some of these lines, which are not accepted into the system. Does this qualify or not?
Let me say, the line. Let me say, for the local Hamiltonian, you can always have this line operator. It's just a product of some local operator along a line. So therefore, existence of a line operator is not contradict with the locality or localness of a Hamiltonian. However, so in the language you refer to is that, put into my language is that when the Hamiltonian whose ground state have a topological order, that means you can find a certain line operator which condense or this Q-form symmetry break. But if a Hamiltonian, local Hamiltonian, have a trivial product state as a ground state, then in your language there's no spontaneous symmetry breaking of this Q-form symmetry. In some sense, so in both systems you can define this line operator. But however, whether this line operator condense or this Q symmetry break or not depend on the Hamiltonian and depend on ground state. So when I say the ground state have a non-trivial topological order, which probably can be translated into this some line operator, membrane operator always have this Q-form symmetry breaking. So this would be really, really interesting. I don't fully understand it, whether this Q-form symmetry breaking can be another language to fully formulate this long-range entanglement topological order. And maybe, but I'm not totally sure. Okay.
So the analogous thing here would be you have some lattice Hamiltonian and some excitations for some reason do not exist. But the low energy observer could still describe them as operators.
Yeah. So again, that's a very, very good example. I don't know whether the answer is question is that suppose you have a standard model with gauge field. And then you demand your standard model do not have a monopoles. Then in my language, that this kind of theory is not UV complete. Or cannot be UV complete. I mean, so any UV complete theory, or if you put standard on a lattice, it necessarily have a monopole. So if you say you have a model which have no monopole, then in my language it's like anomalous. So to make it a non-anomalous, you have to include a full set of this topological extension of this observable. So when you include enough of them, then you find this model can be put on the lattice, and the lattice model would have this full set of topological excitation. So if you only pick a subset topological excitation and require that's the only thing you will have, then you may encounter this so-called anomalous case. It means there is no lattice model can realize this kind of particular property that only this subset of topological excitation are there. Nothing else is there. That may not be consistent. So if you only look at low energy excitation, sometimes the theory may be anomalous. Then you have to include certain finite, very heavy mass excitation to make theory kind of complete. Then the new theory can be put into on the lattice. Yeah. So,
can you explain again why no, but when you don't have monopole, it means that your series
So my statement is the following. Gauge theory, you have a gauge theory, have a charge. Looks like at the low energy theory, you don't need a monopole. Everything is self-consistent. But my claim is that if you want to have UV completion of a gauge theory, you put gauge theory on the lattice. No matter how you do it, the lattice model always has monopole. There's no such a lattice realization with only charge, no monopole. So this is what I mean is that the field theory without the monopole are anomalous, means you cannot do the UV completion. And if you have a monopole, then it's normally free, then you can have a lattice model which reproduce charge and the monopole and the gauge field. But there's no lattice model produce only charge gauge field without the monopole. That's what I mean. Okay, and so this is just this is give this terminology of so-called invertible topological order, which basically means topological order with no bulk excitation, no bulk non-trivial excitation. Yeah, only no bulk anion. So then actually this invertible topological almost trivial because of no bulk excitation. So this can be classified. So this is a table for the invertible bosonic topological order, which is formed by bosons, and there's another table for fermionic invertible topological order. So for example, this P wave Majorana chain is a non-trivial piece of this. So 1 is a trivial, 2 is non-trivial, so it's 2 element, or maybe 0 is a trivial, 1 is non-trivial. Okay. And this P plus P superconductor actually is a generator of this sequence of Z of fermionic invertible topological order is here. And for the bosonic one, it's generated by E8. I don't know whether Nick will talk about this, so I will not talk about this. And this blue entry actually is a cobordism group of oriented manifold. For the top one is a spin-oriented manifold in the bottom one. And there's a relations, and there's some relation, not exactly right. Basically, like this Z2 entry or Z, I think I don't only have Z2. So Z2 entry, they correspond to each other. And the Z entry is a shift by 1 dimension. And so basically, this table have this kind of feature.
So the red ones are theories and the blue ones are cobordism groups?
Yes, the red one is a because of invertible topological order, so therefore the set invertible topological order is an abelian group. So I just list abelian group. So in 0 plus 1 dimension and 1 plus dimension for bosonic case, there's no non-trivial topological order. For 2 plus dimension, this invertible topological order form this integer group. And they're all abelian group. And in 4 plus 1, so those are the red one are really the group for the invertible topological order. And the blue entry is a group, it's cobordism group. But there's this funding shift, yeah, for the Z. So it's not straightforward relation. There's a little bit of shift.
Why are you mentioning cobordism groups? What does that have to do with?
I don't know. And let me scratch my head to see. Actually, this one probably I may understand a little bit better, but this one is, I don't know, yeah. So it's really, so these two are really well known, you know. You guys did it. But the higher dimension is in this paper, which I'm still trying to physically understand. Is that, formulae seems okay.
Obviously, the red ones are Kitayev's periodic table.
This one?
With the real costs.
But there's a Z2 plus Z2, so it's not quite the same. They are not mod 8 periodic. Yeah, it's the higher dimension. The lower one is same, but the higher one is different. Yeah, but they are also interacting. These are interacting one. It's not free one. So it's not quite the same. Yeah. And so in the following, I will try to explain in a way I understand. Cobordism is a little bit tricky to me. I don't know. So the way I try to understand is that this, it really is here. When you have no topological excitation. No topological excitation means that the ground degeneracy on the torus or on any manifold is 1. So that's another consequence of invertible topological order. For invertible topological order, the ground degeneracy on any manifold equal to 1. Okay. So then when you do this geometric phase, the only thing you have is abelian one. There's no non-abelian one because the ground state is non-degenerate. You don't have a phase, not a matrix, not a unitary matrix. So therefore, the only thing you have is this Chern-Simons term. Okay. And so therefore, I try to say, okay, the invertible topological order in 2+ dimension is classified by the Chern-Simons term. And this data is C. That's the only thing we have. This gravitational Chern-Simons term classify this invertible topological order. Then from this point of view, say, okay, we should have a real number because C is a real number. So any real number would give us invertible topological order. Then sounds like invertible topological order should be classified by a real number, not an integer number. Okay, that's naively. But however, using this many times, that's actually also in digraph Witten's paper, this was used heavily. That is the gravitational Chern-Simons term actually is not well defined. Because on the manifold with non-trivial topology, this connection may not be single valued and there's some subtleties. So it's a better way to define gravitational Chern-Simons term is to treat this phase, which is the integration for Chern-Simons term on the 3 manifold, as the integration of a Pointryagin class on the 4 manifold, such that the 4 manifold have a boundary, and the boundary is this 3 manifold. So we rewrite this integration of 3 form as integration of 4 form, but this boundary 4 manifold have a boundary. Okay. So certainly in my case, this omega 3, the gravitational Chern-Simons term is defined as this d omega 3 equal to P1. P1 is a Pointryagin class. Okay. And then we have this subtlety. So suppose we have this 3 manifold. Okay, and we can treat this 3 manifold as a boundary of a 4 manifold. But we can also treat the same 3 manifold as a boundary of another 4 manifold, M4 tilde. Okay, as another 4 manifold. So this different extension may give rise different results. So this definition of from 3 manifold to 4 manifold may depend on this different definition. If you do have the dependence, then that means things are not well defined. And this gives rise to quantization condition for the C. I think I can lower the lights. Yeah. So only when C is certain quantized value, then this definition do not depend on how we extend the 3 manifold to 4 manifold. So this gives us a quantization condition. And this quantization condition can be easily obtained by, say, that the Pointryagin class on the closed 4 manifold, their integration always a 3 times integer. Because these 2 manifolds, these 2 different extensions, M4 and M4 tilde, together form a closed manifold. The difference of the extension is happen to be this, no, we don't need this. The different extension happen to be this integration of Pointryagin class on the closed manifold. So we require that this integration on the closed 4 manifold is always 2 integer times 2 pi. Because this integration Pointryagin number is a 3 times integer. So if you do the arithmetic, you find C has to be 8 times integer, so that the ambiguity from here, from different extension, is always 2 pi times integer. So it's harmless. And that's exactly what we want. Because that really says that the different bosonic topological order invertible one are classified by the C, but the quantized. C is quantized as 8 times integer. And the E8, the quantum Hall state, happen to have a C equal to 8. So that's a generating state. And stacking the E8 quantum Hall states would give us this sequence. So that's perfect. So everything matches. And for the fermionic one, we have a similar idea. You know, we do the same thing. But except that for the fermion, for some unknown reason, which I don't quite understand, for fermion, you have to use a spin manifold for some reason. And I want to understand this better anyway. And there's another mathematical fact. If you say the four manifolds have a spin structure, don't ask me what I mean by spin structure. And then the integration is 68 times integer. There's a factor. What is it? 16 factor 16 difference. So in this case, the C is 1/2. And C is 1/2 happen to be this PiTP superconductor whose edge state is have central charge 1/2. So that's also matched perfectly. So this basically gave us this, this is my understanding why we got this table for 2+1 dimension. So in other dimension, one can use a similar argument to see what kind of gravitational topological term you can write down. And using this, you can classify this invertible topological order. But however, here I want to make one remark. For the condensed matter system, we are always described by Hamiltonians. And we don't care how to define the system in arbitrary space-time manifold. You can see here, I try to define the gravitational Chern-Simons term for arbitrary space-time manifold, which is M3. M3 is a space-time manifold. I try to do that. But in condensed matter, we have a time. There's a time, absolute time there. So therefore, looks like, I don't know, looks like we only concern about the manifold which is have a space, and the time is a circle. So it's a M2 times S1, basically. But we also allow to deform the space, then glue them back. So if you allow this twist, and so that's I'm using this to denote as it's a fiber bundle. The basis manifold is S1, the fiber is S2, and this M2 space. And M2 may twist when you go around the loops. So that's this mathematics citation called as a mapping torus. So in condensed matter, looks like the space-time manifold at the most is a mapping torus. So we only require Chern-Simons term to be well defined on the mapping torus. Okay. And then we try to go through some mathematical literature. If you only say mapping torus, and then this condition, this four manifold is not arbitrary manifold. This four manifold became a so-called surface bundle. And it turns out that the projection class on the surface bundle is quantized as a 12 times integer. And that's led to the result, which is C equal to 2 times integer. So that's, I don't know, that's very intriguing. That's maybe E8 is not the minimal. We can have a Hamiltonian system with a Bosonic invertible topological order with a central charge equal to 2. I don't know, we don't have any example of that. So why I mention this? Because I want to say the following. This kind of argument gives us so-called potential topological order. We only study possible topological invariants. We did not discuss whether all these possible topological invariants are really possible or not, means whether they are realizable by a lattice model or not. We don't discuss that. So for this analysis, it happened to be that all the possible ones are realized by E8 theory or by PiTP theory. But now here you can see, using this different argument for Hamiltonian system, we have a situation that the possible one is C equal to 2 can be. But so far, we still don't know realization. But maybe we have a realization, but we just don't know it. Or maybe this argument has some sickness. I mean, there's something we overlook. So this argument itself is not rigorous. So there's some open issue. For the fermion, you can do the same thing. However, for the fermion, the quantization condition is the same. So we get the same result. For the fermion, there's no difference for some reason. So there's a question? Hmm?
Are you assuming that all these systems are described by a CFT and an edge without central charge, or you get what you meant by that?
Okay. So you don't have to say central charge. Basically, here I use central charge as a coefficient of a gravitational Chern-Simons term. Basically, if you integrate the matter field, you left a response theory to the metric. This response theory may contain a gravitational Chern-Simons term. And this coefficient is called central charge. Then we know that because of anomaly inflow, this really implies that the edge theory should have chiral central charge, which match this gravitational, this coefficient in front of a gravitational Chern-Simons term. So that's how they get connect to the edge state. But for my argument, I don't even need to involve edge states. I just say our response theory contains this gravitational Chern-Simons term with a coefficient we call C, and then we try to go from there to see what kind of C is allowed, are consistent. That's kind of argument. Yes?
Sorry, I'm just confused by, take for example the Bosonic case.
Yeah.
You said for general, for dimensional manifold, the integral is 3 times an integer.
Yeah.
Then you specialize to some particular for manifold, that's M2 mapping-torus.
Yeah, yeah.
With this extra, I mean, embedded in, as a boundary of another variety.
Yeah.
Then it gives 12. Isn't it supposed to be the same?
No. They are more special. So this four manifold.
Just a particular case.
Yeah, this four manifold is found. Let me describe this notation. The basis space is a sigma 2 in any Riemann surface, genus G Riemann surface. And M2 is say another Riemann surface, which is a fiber. So this is a fiber bundle where M2 is fiber, sigma 2 is a base space, and this semi-product is some fiber bundle. And then for this type of four manifold, this is a 12. You know, I dig through a lot of math literature to get this number. And so this which give us different results. So I'm kind of puzzled. You know, it's very, very intriguing. That is the Hamiltonian system and the Lagrangian system might be different. And I don't know. Yeah, this is the one possibility. They might be different. Yes. They're all orientable. Yeah, I'm sorry. So the thing I discussed all orientable. Yeah. Yes.
Why did you consider something like the M3 type system?
Where's M3?
So why did you consider cobordism?
Yeah, this is this one, you mean?
Yes. So in this spaces M2 and this one, and you're considering the cobordism, right?
No, I don't know the cobordism. I just want to say that.
Just saying that region. So yeah.
Oh yeah. Oh, I know. I skipped something. So from here to here, there's something which I skipped. You know, there's a more thing to go from here to here. Yeah. Why? But I just give you some flavor. What kind of thinking will go into it? And because this table, if you just look at the table, it's very sudden. You know, we don't know where it's come from. But if you think about this, how to define gravitational Chern-Simons term, you get some taste. You know how to get this table. Yeah.
So Wayne, how much more? We're getting a little bit short on time.
Yeah. So when should we end? How much time I have?
5 minutes.
Okay. Yeah. Very good. So so that's okay. Yeah. So then. So far we described this a simple one, I mean invertible one with no bulk topologization. So now let's consider the harder one, so the one with bulk excitation. So to consider that, we will try to quotient out invertible one. We just say, let's ignore this invertible one. We only consider topological order up to the invertible one. So those topological order are described by this ST matrix. So now central charge is no longer important. So we only have, so this ST matrix is no longer one-dimensional because we have several topological excitation which happen to be the ground state degeneracy and the torus. So the dimension of this ST matrix, this non-abelian barrier phase, is actually happen to be equal to the number of a topological type, which is bigger than 1. So we have some kind of 2 by 2, 3 by 3 matrix. And certainly, those are unitary matrix. And we mentioned that the claim is that all this 2D topological order up to invertible one can be fully characterized by this 2 matrix. But certainly, not every ST matrix gives us topological order. Only some special one give us topological order. So therefore, we need to find the condition on the ST matrix so that this kind of ST matrix is a valid data which correspond to topological order. And so there's a, the Andrew again talked about this. So there's a lot of conditions on the ST matrix. In particular, in the last lecture, you see that from the S matrix, if choosing certain basis, from the S matrix, you can get so-called integer number. This is a von Lennep formula. So this combination of S matrix is an integer. That's a magical relation. We know where it comes from. S matrix is a non-abelian barrier phase, some unitary matrix. But somehow, in order for this S matrix to describe topological order, it has to satisfy this magical relation. This combined give an integer. Certainly, this set integer also satisfy other conditions because those integers are kind of fusion coefficient of these topological particles. And the T matrix in this basis can be diagonal. So diagonal element basically is a spin of the quasi-particle with a shift of central charge. And then you can have a bunch of relation to constrain the SNT. So this is one page is relation. The second page of relation, there's a lot of work from mathematicians and physicists and string theorists, to understand those relations. So when you put this all relation together and solve that numerically, and you get this table. So those just find those ST relations. So so that's written in terms of a quantum dimension and spin. The spin basically is the diagonal element of a T matrix. The quantum dimension is.
I'm confused by these statements because the S and T matrices are not sufficient to determine the modular tensor category, which is how you really classify the
Yeah.
topological phases.
Very, very good. Yeah.
So S and T matrices doesn't give you a table that classifies topological phases.
Yes. No. So this is so certainly to really classify modular tensor category theory, one should do much harder work. Do this F symbol, particle identity. But solving particle identity is too hard. I don't know how to do that numerically. And then there's we call the simple version of this modular tensor category based on SNT matrix. This simple version is not known to be equivalent. So therefore, this table may have errors, but error in the following sense. That is, some of the entry in the table may be fake, may not correspond to anything.
Some of the entries may actually split into distinct topological phases.
That's also possible, but
I'm fairly sure this is the case, actually.
That sounds like that's the only thing that's possible.
Examples of low rank.
if you quotient out this invertible one,
Talking about the unitary modular tensor category,
that's right.
which is the ones of real interest. So you can take a set of fusion rules and S and T matrices, you still find distinct solutions to all of the Mohr-Seiberg consistencies.
Yeah, and so there's an example of that. Actually, I don't know that.
Well, we just look in Wang's paper with the, up to rank 4. I'm sure we'll find examples there.
No, actually, this is a, here the rank 4. This rank 4 completely agree with Zhenghan's classification.
You have to go a little bit further, but I'm sure you will find examples.
I see. This could be possible, and yeah, and some entry may be fake because the list of conditions we find may be not enough. We may have actual conditions, and then another thing is that you mentioned really that this one entry may correspond to several topological order. that means ST, the data is not enough. We need to add more data. And so thank you for pointing it out. So this is a kind of simplified version, which we can produce a table. And for simple case, let me put it, for simple case, it's kind of work. And maybe let me put it this way. I think I feel this way is simpler, it's easier to produce a table. And if this formulation is not enough, so one want to get the next step. So do we want to introduce new data? Then what is new data? And then by adding this new data, we'll make things better. And that's a precise point. I try to avoid solving Panther equation because Panther equation is kind of hard to solve. So this is but anyway, so this is a simplified theory, and kind of pseudo theory, you can say. And so maybe let's make one last remark is that there's maybe that's not making this remark. Let's just say you can do the same thing for the fermion actually, and you can get a table for the fermion, but with the similar remark. This is still a simplified theory based on ST matrix, and you can get this table, and yeah. So maybe I will stop here.